Okay, so I'll just catch up to where we were. We're up in Browning, Montana, and we're also giving a mechanics lecture in Sri Lanka. So what I first started the experiment with was just something simple, and we can either pull it in tension or we can push it in compression. So what I'm showing so far is that the harder I pull in this direction, the more force I feel. This is tension. And then this direction down here, I think you can see that okay. This direction down here is compression. Compression. Sorry, that got a little bit sloppy. And then we also showed that if I tear something like this, it's called shear. And I'm just going to put shear off by itself over for a second. Shear. Okay. Now, what happens if I just keep pulling and pulling? Eventually it breaks. And I end up here, which is called fracture. Sounds like Bailey's talking back there. Okay, so these are the ways things can break or fail mechanically. They can either fracture in tension. We showed that it's usually harder, at least with a piece of paper, to compress something and make it fail. I could do it if I've got a box like this and I keep pushing and pushing. Eventually it'll fail in compression. And that's down here. Okay, so those are the three primary modes of pulling something apart or breaking something. Now, why is this important? And I'll start off, I'm going to try to tie in the solar a little bit with the wind, because this is important for installing solar panels. We're up here in Browning, Montana. It's very windy, as we know. And I'm just going to go ahead and I'm going to put a solar panel on a roof, and I'm going to show the force it's going to take to blow that panel off the roof, and then I'm going to go and show a kite flying and show how you want your solar panel to not become a kite. So we'll just do those two things, and I'm also going to show the amount of energy in the wind. So let's just take something simple here. Here's a house. And what's the best place to put this this panel? So let's have the panel just sitting like this on the roof. And let's say the wind is coming in with some velocity. Now I know if I don't have the panel connected here and here, it's going to blow away, right? So we need some kind of way of attaching the panel to the roof, and we're going to do that with a it's like a nut or a bolt or something. I'll just use a couple of pens. So these pens that are sitting here on the roof, if they break, they're going to go from being in one piece to shearing apart. So what we're going to try to do is figure out how much force that is. So here's the velocity of the wind. The panel has some area. The panel also has some coefficient of friction. So what we're hoping we don't have happen is that the panel is forced off the roof, and so we need to have strong enough attachments here and here. So first I'll give you the force on the panel. So the force equals 1/2 rho C A, and then this last part is the most important. Last part is most important. It's V squared.
The language of the resolutions.
So that's how much force is actually acting on the panel. And so the V squared is the velocity of the wind. So the faster the wind is blowing, the more force. The area I just showed you is how big the panel is. So the bigger the panel is, the more force it feels. And we've seen that with the kite. And I'll show you that with the kite shortly. This C right here, that's typically a number somewhere between 0 and 1. And that's based on the shape of the panel. So if the panel is sitting up like this, with all of its surface area, that's a C of 1. If it's sitting closer like this, where the wind's just blowing past it, that's a C closer to 0. So it's a factor of how it's heading. And then this number, that's the density of air. That's the density of air. So let's just do one simple problem where we calculate the amount of force on a solar panel. Pretty simple. Okay. So the density of air, and we'll use the units. And I think I can fit everything down here.
General or something.
So obviously it's easy to deal with the 2. We'll just leave that in the denominator. So we'll just put the 2 down here. Anybody know the density of air? I need to know how many pounds per cubic foot or how many kilograms per cubic meter. Does anyone? You might be thinking of air pressure, which is maybe 14 psi, but I need to know how much a cubic meter of air weighs, how much mass is in that cubic meter. We don't usually think about mass or air having weight, but it does. Air weighs about 1 kilogram per cubic meter. Now we're gonna assume kind of worst case scenario, and we're gonna assume that our panel is just the wind's just blasting right at it. That's kind of the worst case scenario. It's kind of like the panel's a stop sign, and so we'll just assume it's 1. And when you're making your estimates, you say, okay, what's the worst possible case scenario? So let's just let that be 1. That's my row. This is my 1. Okay, so Rob, what's a good area to use for a panel? You've got some specs over there for your Cool PV.
Yeah, the Cool PV panel is about 70 inches by 65 inches by 40 inches by 4.5.
Okay, so what we're going to look at the specs here, and this is the size of the panel right on the bottom. We'll see how big that panel is. So if it's bigger, it's going to experience more force. If it's bigger, it's going to experience more force. And so for now, let's just say that the panel is 2 square meters as a reasonable estimate. So if the panel is 2 meters squared, obviously that's bigger. It means we'll need bigger bolts here. The bigger it gets, the bigger the bolts we'll need to keep it on the roof. And then finally, what's a reasonable wind speed? So Professor Bowe has been taking some wind speeds here. What's a good speed that you've seen so far?
Average 18 kilometers per.
18 kilometers per hour. Okay, so we'll take kilometers per hour and turn that into meters per second. So we'll do that right down here. So 18 kilometers per hour. Can you guys with the calculators help me turn kilometers per hour into meters per second? So I'm going to try to do that. So I know if I've got how many meters in 1 kilometer? How many meters in 1 kilometer? 1,000. Thank you. So if I've got one kilometer down here, I've got 1,000 meters up here. So I multiplied by 1. And then how many seconds in 1 hour? How many seconds in 1 hour? How many seconds in 1 hour? If I wanted to count,
Is it 1,200 or?
well, how many seconds in a minute? 60. How many minutes in an hour? 60. What's 60 times 60?
Well, it's hard to add. Let's go a lot.
The answer of the day, 1,200. No, it's 36. So 60 times 60 is 3,600. So if I've got 1 hour up here, I've got 3,600 seconds down here. Okay, so somebody do 18 times 1,000 divided by 3,600. Did you bring your phone in today to do that?
Just yesterday, on a project.
Can someone do that on their cell phone for me? 18 times 1,000 divided by 3,600. What's that?
Investors.
5? Is it only 5? That's pretty lucky.
Much like
Five?
the
Okay,
wind,
cool.
we can do.
Okay, so 5
Study.
meters per second. And then we're going to square that. Okay, so now I need to take 5 times 5, that's 25. I've got a 2 here, the 2's cancel, so we can do that. We can do that.
The full.
And then I think it's just 25, right? I think that's what I'm coming up with. So 5 times 5 equals 25. So this actually isn't too bad. This isn't as bad as I thought. And we end up with kilograms. We end up with kilograms. And then how are we doing on meters? We've got meters squared. It's meters to the 4th divided by meters cubed. Kilograms per meter. Or no, on the top. Oops. Just get rid of that. Set it over there. Kilogram meters per second squared. Okay, so what that is, that actually comes out to be 25 newtons. Somebody's got to tell me what 25 newtons is in pounds. I can't remember. Can you guys get on the, actually, let's do it right here. Let's get a new browser up. 25 newtons. So let's just do newtons to pounds. So this is a lot like what we did yesterday. Remember we converted calories into joules and joules into BTUs. So we're just going to do newtons to pounds. Newtons to pounds.
Debt service. So.
Okay, so 25 newtons. It's about 5 pounds of force. It's a little lower than I would have expected, but that's what it comes out to. 25 newtons equals 5 pounds. Okay, so that's one way to get at the mechanics of a wind blowing on a solar panel. So kind of simple, and then we would come back. So force equals 5 lbs. What would happen if we doubled that number? What would happen if we doubled the wind speed? Is the force going to double? Who says the force is going to double? Who said it's going to be less than double? Who said it's going to be a lot more than double? Let's try it. So what I'm going to do, I'm going to take that 5 and turn it into a 10. I think I've got some room here at the top. I'm going to take that 5 and turn it into a 10. So if I get a, let's see if I get a new, edit, select all, edit, copy. That's fun. So now I'm going to take this and let's try this guy. So all I'm going to do is double that wind speed. I'm just going to double that wind speed. It used to be 18. What's 18 times 2? 36. So 36. This goes to 10. And so now what I need is 10 squared. What's 10 times 10? It's 100. So now this goes to 100 newtons. Let's go back and see how many pounds that is. Let's go back and see how many pounds that is.
Guys, I'm working.
So we were at 25 newtons a second ago. Now we're going to 100. 22 pounds. So who said the force was going to double? All right. Who said it was going to more than double? That was your chance for the starburst. I know somebody said it. So the fact that the force goes up by the square of the velocity means that the faster the wind blows, the force goes up much more quickly. So instead of going just to 5 pounds, we're at 22 pounds. It goes up by a factor of 4. So the wind speed doubled, the force quadrupled. And that's you probably feel it. So there's 20. When we went from we went to 5 to 22 pounds. All right. So that's what I wanted to cover on mechanics. When we sit down later, we'll talk with the wind teams. We'll talk more about how much mechanical power you can expect to see flowing through your system. So. Everybody, thanks. I'm just going to sign out here with Sri Lanka. Any questions at all on that? Thanks. Yeah, okay. All right.
Let's go out and do our culture thing.
All right, guys. Thanks a lot. Hey. I don't know if John is here or not this morning, but were you able to get to those inverter questions? Because there was that one last sheet on the inverters that I don't think we got to. I'll show you. I'll show you what I'm talking about. I'll show you. I think Brandon's ready for everybody out there.
Is he?
I think he is.
Check?
I think that's what Tim said. Just why don't you check, and then I think everyone can go out and do the cultural.
Just for the hook. That's intriguing to hear. That's intriguing to hear. Well, those are I don't know if you've been down on the Navajo at all, but
Outside.
Technology service provided that have technology for these remote systems. So those are all items that yeah, you know, the realities,
Okay, I'm sorry, I'm trying to tell John Bailey to leave the call. Okay, I'm gonna go and share the screen with you.
Turkey had more time, but you know there are some more. I don't. I do know there are some more remote settlements or more remote communities.
Can you just do that on Skype?
Probably.
It's on Google Hangout.
Oh.
I'm trying to, I don't know how to get somebody to hang up though. There's John Bailey's out there. I need to hang him up.
That's servicing that area.
Google Hangouts?
Well, yeah, there's just not that many controls in here. I told him to, so this is him.
I thought there was an in session there when he logged out. Is that her there? She's still there?
Yeah, this is but there's a way that I can add somebody up here.
Yeah.
Yeah.
And here's the settings. Bandwidth, general, video, microphone, communication.
There's nothing on that telephone there?
This guy? I think this just hangs the whole thing up.
Don't you want to just quit?
Well, I want to show her something, but I want to kick him out.
So that's definitely an opportunity.
I'm gonna go up.
Okay, I'm gonna call you right back so I can hang up on John. I'll call you right back. I'll be right back. I'll be right back. I'll be right back.
Okay. Okay.
Way to make sure that maintenance happens. I would just.
Okay, I think that's a little bit better. That's a little bit better. So I wanted to cover one more thing. I wanted to cover the inverters.
I didn't understand.
The inverters. Oh, this back here.
I did understand got you.
Yeah, this is something that I guess the bottom line, what I'm trying to show is that if we have our if we have the solar panel here, if this is the solar panel and the wind is blowing, it can create so much force that it pushes it or breaks it. And so this equation, this equation is for force. Force, it's how hard you push or pull. It's force. This is 1/2. This letter right here is density. It's spelled D-E-N-S-I-T-Y, density. And it's the letter rho. It's a Greek letter rho, R-H-O. And it's how heavy wind is. It's how much mass there is in the air. And it's 1 kilogram per cubic meter. And then C, facing you, C is 1, and that's 0. 1, 0. So I put a 1 here. And then A, this is how big the panel is. So it's the size. It's the size, the height and width of the panel. So I wrote it as 2 square meters, 2 square meters. And then the last one is the velocity. It's how fast. It's the speed. And I wrote 10 meters. 10 meters per second. On this one I wrote 5 meters per second. And then I just multiplied. So 1 times 1 times 2 times 10 times 10. The 2's cancel, and I'm just left with 100. So I have 100 kilograms times meters, because I have meters times meters times meters times meters, meters to the 4th, divided by meters cubed is just meters, and then seconds is in the denominator. So 100 kilogram meter per second squared, that's 100 newtons, that's 22 pounds. So that's so those calculations are important for mechanics, for understanding how things break and fail. Okay, so let's go back into inverters, because I wanted to show you that. And typically the inverter, by the way, the inverter sits on the back of the panel. I had one in here. I think it's outside now. But if you go from, again, you know this already, if you go from DC to AC, you need an inverter. DC to AC, you need an inverter. So let's do that calculation now. I'm looking it up. I think it's lesson 8. This was a very long one, I remember. There was a lot here. It was lesson 8 that we did, I think March 29th, or May 29th. Let me look. I think it was all the way at the bottom. Yeah, here it is. Okay, so I'll share it with you. Share screen. Whole screen. All right, so this is PV string sizing. Okay, so what we're looking for is the maximum DC voltage output, and this is for the Sunny Boy 3000, page 102. And let me see if I have that. I will look it up. Let me just look that up online. It's the maximum DC. So this is the inverter. Now we just need to look up the specs. Maybe it's here. Let's see. It's the installation manual, and it's 100 pages long. Okay. So when you receive new equipment, it'll have a manual. Always very important to read the entire manual, especially for safety. If you take some technology out and don't follow the instructions, it can result in injury. Or it can also result in damaging the equipment. So it's now loading. And I'm just going to download this to my computer. I'll save it. And I'm going to save it in my courses. Scroll down here. Sri Lanka. Oh. Look, okay, I have that. This might be a different one. Slightly different, but now I have two of them. Now I have two of them. I forgot I put it right there. Okay, that's okay. So let's go through. I'm going to see if I can do a search in here. All right. So here's one manual. Here's the one I just downloaded is here. This is the other one. I'm going to open this. I'll open this manual with Adobe Pro. So now if I go back, I'm looking for maximum DC input voltage. So obviously if I have an inverter, it can't accept an arbitrarily large number of panels. It's got a maximum limit. It has a maximum capacity. So let's see what that is. And I'm going to try to search for the word maximum. Those are always good things to know. Maximum temperature 45°. That's good to know. Let's keep looking. Maximum wire size is a number 6 wire. And just excuse me 1 second, I'm going to go out in the other room. Guys, I'll be right back with you. I'm just going to wrap up here. Okay, so let's, I'm back. I'm going to go see if I can find the maximum voltage. Verify the polarity, applying the open circuit voltage. So you do not exceed the maximum input range. It will cause irreversible damage. So let's find out what that is. Okay, so this number, 7 watts, that's how much it takes to run the inverter itself, which is pretty low. Looks like if you're taking data, you can have 50 inverters. That's a lot. Okay, this is the maximum frequency. Operating mode, maximum power. So this is, we do need to know this, maximum power point, but there's no number there. Let's keep going. Maximum temperature for the fan. That's not it. I'm going to keep looking. Here we go. Okay. Maximum DC power, 3250. There we go. We finally found our answer. 3250 watts. 3250 watts. Okay, so specifications, maximum DC power, 3,250 watts, or maybe easier to think about, 3.25 kilowatts. Okay. And now we need the minimum MPP voltage input. Minimum voltage MPP input. Let's search for the word minimum. And I'm going to go a little faster this time. I'm going to go a little faster. Okay, and I don't see it here on this. Let's look for MPP. MPP. Usually this refers to maximum power point. So remember, we're looking for the power, which is volts times amps. MPP, MPP. I don't see this one. I don't see this one. Let's look in the other manual really quick here. So this was the SB 3000. Let's look at the SMA. And I'm going to open that with Adobe Acrobat. So this is a different one. Control F, MPP. MPP. All right. Okay. So I'm sorry, I can't find that one. I'm going to go ask my assistant Tim. He might know this better than I do. Okay. Module open circuit voltage. Let's look for that. Is somebody calling? I don't know. Okay. All right. I'll go back in to the quiz. So we're looking for the open circuit voltage. Open circuit voltage. Let's use this one first. So here's the AC input voltage. Open. Let's see if we can find open circuit. Inverter specifications. So the maximum input short circuit current, power consumption, DC, weight, compliance. Huh, I'm surprised. Peak power track. Yeah, I don't see that one. That's another question too. Oh, so this is for a module. Okay, good. Let's see. Oh, here's the modules. Yeah, let's look for these guys. The REC 240. REC 240. So let's go look for those. REC 240. Let's find that. So we already did the inverter. Except I was not able to find the minimum power point voltage input. That should be somewhere. I just couldn't find it. But let's go for the module and try to find the open circuit. So let's look for the REC 240 panel. I'll go back out here, do a search. Solar design tool. All right, here we go. So here are the specs for this, and we'll just pull it straight off of this page. We'll pull it straight off the page. And so we're looking for the open circuit voltage. So that's VOC. 36.8 volts. 36.8 volts. Maximum power voltage. So this is volts max power, 29.7. 29.7 volts. Temperature coefficient. So if you remember, the open circuit voltage is greater than the maximum voltage. That might seem a little bit counterintuitive, but let's just go and look at a curve. Let's go and look at a curve. This is a good one. So you can see this is the open circuit voltage is out here, and the maximum voltage is here. But it's this portion under the curve that is our power. So remember, power is volts times amps. So this is the the total power under here. So the open circuit voltage is greater than the voltage at the maximum PP, maximum power point. Okay, so that's similar. Okay, temperature coefficient of voltage. Temperature coefficient. So there's three. Temperature coefficient for current, temperature coefficient for power, temperature coefficient of voltage. And this is negative 0.099 volts per Kelvin. So negative 0.099 volts per Kelvin. So if I have, so let me just do a little equation. Delta V equals alpha delta T. So I'll make it look, I'll make these into symbols. So if I have alpha equals 0.099 volts per Kelvin, and let's say delta T equals, let's just say we go from 20 Celsius up to 40 Celsius. Let's say that equals 20 degrees C equals so let's say a change of 20 degrees C equals that equals 20K. So now we can solve our problem. Delta V. So we'll take this number, copy it. We'll take this number, copy it. We'll do our math. So 0.099 times 20 equals 1.9 equals negative 1.98 volts. So what this is telling us is if the temperature goes up, if the temperature goes up by 20 degrees Celsius or 20 degrees Kelvin, the voltage goes down by 2 degrees. So if we go back here, so that what this means is when it gets hotter, the panels don't work as well. Right? So if the voltage goes down, so does the power. And we could do the same thing. We could say for every change in 1 degree Kelvin, we lose 0.4%. So this is why it's good to keep the panels nice and cool. And one thing I just want to tell you, this is why we're very excited to get this new set of panels in. Let me show you this one more time. I think they're going to arrive today. I think they're going to arrive today here in Browning. So let me go and show you these one more time. They might arrive Monday. Let me show you. We purchased some of these. So if the So if cool water goes in here, if cool water goes in, it makes the panel work better. So we need to keep the panels nice and cool. Okay. So let's go back to our questions. So we found this. I did not find the minimum. I'll have to email that to you. Okay. So let's see if we can get the rest of them. What is the max voltage open current for a series string of 13 modules at standard conditions? The maximum open circuit voltage. So in this case, and I might have to have Tim verify this for me, but I'm going to take a crack at it. I'm going to take a crack at it. If they're in series, we'll just assume they're in series, and we have voltage OC max equals 13 times VOC equals 13 times 36.8 volts equals, so 13 times 36.8 13 times 36.8 equals 478.4 volts. 478. That's pretty high. That's a lot of voltage. That's pretty high. Okay, so the next question is, what happens to the module voltage as it decreases? Well, we just saw that up here. As module temperature increases, module voltage decreases. Oh, let me do it the other way. I was thinking of it in reverse. So as module temperature decreases, module voltage increases. All right. Okay. What relevant PV design temperatures for Missoula? Extreme high temperature. This is going to be 110, maybe 120 degrees Fahrenheit. And let's go and do the conversion. 120 F to C. 120 Fahrenheit is 49 Celsius. Let's just call that 50 Celsius. So not all panels can go that high. Extreme low temperature is maybe minus 30 F, minus 30 degree F. Maybe you've never seen that. I don't think you've ever seen it that cold in Sri Lanka. Minus 30 F to C. It's minus 34 Celsius. It's very cold. Equals minus 34 C. So if you come to Missoula, maybe you don't want to come in the winter because that's quite cold. All right. The 2000 NEC, so let's look for that. 2000 NEC, 2011 NEC. Okay, so this is the safety handbook for electricity. And I would like you to download a copy, please. Please download a copy. Free download. Here we go. Free version of the 2011 NEC. I think there's another one. I'm almost positive I have a copy here somewhere. Let's see if we can find it. How to get a free copy. Free copy. So the NEC, it's published by the NFPA, which is the National Fire Protection Association. And the point here is that if you install your electricity incorrectly, you can cause fire. We might also try the 2014. These come out every 3 years. Let's look for the 2014. It might actually be easier to find. You can also buy it. Kindle. Well, it's $70. I don't know if John Bailey has some room in the budget, but maybe you want to ask him to purchase this. And I would say get it in a hard copy format. Okay. Well, hey Tim, I got one quick question for you, a technical question. I'm not familiar with the minimum MPP for an inverter. Is that something
Right.
you come across?
Oh, yeah, for sure.
What is that?
They have, your inverter won't kick on below a certain voltage.
Right.
And it won't track below
Right.
a certain voltage.
Okay.
But it literally will not even turn on for less than
Okay.
that voltage.
Yeah, I was just kind of searching through specs, for example. We were just looking through, there's AC input, frequency.
So your minimum value is going to be your 200.
Okay.
And your maximum is your 400.
Awesome. Okay, perfect.
And it
perfect.
will not turn on at 200.
Right.
And over 400, it'll keep running,
Mhm.
but it won't PowerPoint track.
Gotcha.
90% of the inverters out there, though, these are all grid tie.
Mhm.
90% of these inverters will run all the way up to what their max voltage is. So,
Okay, cool.
because what they're saying is, why do I need to track it if it's, even though the thing will take 600, why do I even need to track it if it's over 400? It's working.
Okay. Awesome. Thanks. I'm almost done here. So this is that's the minimum. It's not specified as such, but it's the bottom of the range.
Right.
Yeah. Okay. I'll be right with you there.
All right. You go over and start working on our. Yep, absolutely. All right. So make sure your team processes with you.
Okay, so I'm going to leave this last question to you. So if you all can wrap that up. if you all can wrap that up, I've got to get out here to my next class. But thanks a lot there, Grace Center. I've got at least a picture of the mountains behind me, and off to my side over here, the real one. So maybe next week we'll take you out there a little bit. Okay, thanks. Goodbye.